Hello, everybody. Let's get started. This is the survey strategy status update session, which we have at every Rubin CW. My name is Federica Bianco. I am Deputy Project Scientist for Rubin Construction. And as that, one of my main responsibilities is to lead the Survey Cadence Optimization Committee, which is recommending survey strategy to the director. Clicker for changing slides? Is there a clicker for changing the slides? No. Okay. I want to remind you that this meeting has a code of conduct that ensures that this is a safe place for everybody. So please remind yourself of the code of conduct, which you can find at this QR code, and respect it at all time. We have 3 points of contact for code of conduct violations. So if you shall witness or experience a code of conduct violation, please reach out to Sandrine Thomas, Andrew Connolly, or myself. Our emails are there. You can reach out on Slack as well. Please respect people's level of comfort with physical contact, which is indicated on their badge by stickers if they wish to put the sticker on it, as well as be considerate of people's social battery at this meeting. We do have, at these kind of meetings, we do have a lot of social interactions that might be challenging for some people. Also, there's a lost and found at the registration, the RCW registration desk. If you're like me, I've already lost 2 things. So that's a useful piece of information. No, neither. I lost a bracelet and a bottle. So if anybody, just like come to me. If you are a virtual participant on Zoom, please stay muted if you're not speaking so we don't disrupt with noise. In-person participants, please wait for the microphone to speak up. We will have obviously time for questions. There's also a Slack channel, which Peter is monitoring, right? More or less, he's going to be monitoring in a couple of minutes anyways, which is not the right one here. But today is day 3, Wednesday, 10:30 survey strategy. There's going to be, if you want to ask questions on Slack, please go ahead. We'll pick them up over time. We'll also have time for live questions and interactions. Raise your hand on Zoom, etc., etc. I'm going to add my own specific mention to these recommendations of rules of engagement. I really like a word that is used by Ruha Benjamin, who is a professor at Princeton who studies society and AI, and she uses the word "astopia" to indicate a community that we build with our consciousness about how we treat each other. So let's make this one an astopia and be respectful and thoughtful with each other at all time. I'll have a quick outline of the talk. We'll talk about the survey design process. Most of you are familiar with it, I'm sure, but there might be some people who have not been to this session before. So we'll tell you how Rubin is designing the survey strategy with community participation. We'll talk about the most recent simulation, which most of you have not seen. In fact, probably nobody except for the members of the committee. That's version 5.0. And we'll talk about specific features of this simulation and specific things that this simulation does and explores, including in particular the deep drilling fields and templates. We will discuss some questions that remain open, and those are the focus points that the SCOC is still working on live at the moment or will be working on in the future. The first thing that I want to mention about the survey strategy design for LSST is that this is a truly unconventional and innovative process. The degree of participation of the community in this process is unprecedented. We called it in this paper, which describes the way in which Rubin has approached the design of the survey, a pioneering process of community-focused experimental design. We described it in some length in this paper, which you can access at the special issue of the Astrophysical Journal supplements on Rubin Cadence. And I want to highlight how proud I am that this survey has a special issue even before data had appeared. Now we start to have papers with data, but papers on Rubin LSST appear on this special issue for several years now. If you don't want to read the paper, there's also a YouTube video where we discuss it with the editors of the Astrophysical Journal. The protagonists of the story of how we design the survey strategy are many. The survey strategy team is a key element of this process. The survey strategy team right now, Lynn Jones, Peter Joachim, and Eric Nielsen. Lynn is online, I think. I didn't see her, but I trust that she's online. Peter and Eric are here in the front row. They design the survey strategy. They design the infrastructure that enables survey strategy simulations. They also work on the scheduler that runs the telescope. They designed an interface for the community to interact with the simulations of the survey strategy. Those two key pieces of infrastructure. Three pieces of infrastructure are the OPSIM, the simulator for the survey strategy, the scheduler, which actually runs the survey strategy, which is used in the OPSIM, and the metric analysis framework, MAF, which is an API, Python-based, that allows the community to interact with the simulations. And we now have thousands of simulations of how LSST could conduct, how Rubin could conduct the LSST survey. The scheduler, which I mentioned, is actually already in use. It doesn't only interact with the observing strategy, with the simulator, but it's actually now being used, and for a couple of years already, both to run Oxtel and now to run the telescope, the main telescope. It's running the science verification, and it will obviously run LSST. We will have a lot more information on this in a second session on survey strategy today. In the afternoon, we will talk about more details of the feature-based scheduler, but also, and in particular, how we will monitor the survey strategy throughout operation, how we're monitoring it now, and how we will continue to monitor it throughout operation and interact with the community at that time. The other key people in the survey strategy design are the members of the Survey Cadence Optimization Committee. You see them all here. Some of them are in the room. Who did I see? Kat, Rachel, Louise, and I saw Sarab online. And if anybody else is there, please raise your hand or wave or let the people in the room recognize you. The Survey Cadence Optimization Committee is the hardest committee working on Earth, possibly. It's a really hard job. They take input from thousands of community members. Well, I don't know if thousands, but they've taken input historically from hundreds of community members in various forms, in the forms of papers, direct communication, reports, solicited and unsolicited, and they put them together into a really difficult exercise of optimization such that we can build a survey that can maximize science throughout across all scientific topics that LSST wants to do, and surprise, surprise, LSST wants to do all scientific topics. So it's a really hard job, and they're a very dedicated committee, which works really hard. So I want to extend my thanks to them. Also, I have a few past members. Some of them are in the room. Knut, I think I saw him walking forward. Thanks to them as well. We just had well, not just really a year and a half, we had a few members rotation. How does the process work? So roughly started in 2014 when the OPSIM was created, the software, the OPSIM and MAF were created that I was mentioning earlier, and some simulations of how LSST might look at the sky started appearing. At the time, 14 simulations. Phil Marshall at the time led a community effort among the science collaborations to review these simulations and see how well they would do on specific science cases. We call that the COSEP. It's a paper which you can access at this link. And that increased the number of simulations by embracing ideas that were in the paper to 16. Then we called people more broadly to respond to these simulations and evaluate them for their science cases. We had 46 community-wide papers with hundreds of contributions, at which point the SAC reviewed all these papers and decided that they needed a dedicated committee to continue doing this job. So that's when the SCOC was instantiated. The simulations rose to 173, more community contributions, 39 Cadence notes, more simulations, more community contributions, more simulations, rinse and repeat over and over again. At each of these OPSIM benchmarks on this slide, you see the version of the simulations changing, OPSIM 1, OPSIM 2. Right now we are at OPSIM 5. Spoiler alert. OPSIM 4 was presented and discussed in extent in a report, the phase 3 report of the SCOC, which you can find here. In baseline 4.0, the link at the bottom is the session, this session from last year, Rubin CW. So you can watch that to catch up on the baseline 4.0 and on the report that describes it. A lot of things came into place at that point, but it left a few open questions. Deep drilling fields, what should be the detailed observing strategy intranight and across the seasons? What will be the year one observing strategy? How will it be different from other years since we had to collect templates? And should rolling happen in 3 or 4 cycles? I'm going to tell you right now, we're not going to talk about the last point. This is something that the COC has time to focus on throughout the first year, because we don't have to decide that until the beginning of year 2. So I don't have any updates on that. 3 cycles increase uniformity, 4 cycles may increase time domain throughput, and we're still discussing it. All the other points, we're going to close the loop on. We're going to close the loop on, and we're going to present the new baseline strategy, which is baseline 5.0. There it is. So let's dig right into baseline 5.0. Unless anybody has a question on the process, we could answer a quick question. So moving on to baseline 5.0, what are the changes from the previous baseline? So in baseline 5.0, it's for the first time we have included a single snap visit in the baseline. We have carried on simulations with single snap visits throughout, but they were never in our baseline. We now have included that in the baseline simulation, which means the default becomes, the default expectations becomes that we will run with single snaps. What is single snaps? Originally, we thought we were going to take images in 2 15-second exposures to be combined. So every visit will be 2 15-second exposures. More recently, we have discussed the possibility of switching to 1 30-second exposure. That provides a very significant efficiency increase of about 6 or 7% over the entire survey. So it's a really good idea to improve the efficiency of the survey, which obviously improves the throughput on most, if not all, science cases. We have adopted 38 seconds visits in U-band. Actually, I think that was also in baseline 4.0, but it's a relatively new change in our visit. Oh, I know why it's there, because the other filters are 30 seconds and U-band is 38 seconds. We have significant changes on the deep drilling field survey strategy. We have created a new approach to deep drilling fields, which we call the Ocean Earth Survey Strategy, which we'll talk about in extent. We do have TO follow-up strategy updates. We'll talk about that briefly. We have a couple more changes that are less perhaps familiar, less expected by the audience. We have changed the readout time to 3.07 seconds from 3 seconds. With the efficiency increase that is brought on by the single snaps, it makes sense to extend the readout time if that improves the readout noise, which it does. So at this point, we have integrated this new readout time, which is slightly longer, into our simulations. And we have reduced the efficiency, we reduced the slew speed. So overall, the efficiency with which the telescope moves from one image, from one position to another. We have done them to be conservative. We used to run the simulations with a 70% speed, which is what's expected that we will reach, but we don't, we want to be conservative on this because at the moment the telescope doesn't reach that speed. So we wanted to ensure that we weren't over-promising efficiency. And we expect that at the beginning of the survey, the speed of the telescope will be somewhere in between what we're simulating now and the 70% that we used to simulate earlier. So this is a sort of slightly conservative approach to efficiency, to observational efficiency. So overall, the version 5.0 of the baseline does a lot of great things. Starting with, it increased the median number of visits per pointing, while it keeps, well, even if we have a conservative estimate of time available on Sky, and we increased the area covered by a minimum of 750 visits. So here you see the footprint of 5.0. You can't see any differences from the footprint of 4.0, at least by eye for sure. But you can see on this plot the number of visits and the area as a function of area, the area covered as a function of number of visits. And the baseline 5.0 is slightly to the right of baseline 4.3.5, which was an update on the baseline released last year. So this gives across the board improvements for all science. More visits means more depth and higher cadence for all. So all science benefits from this. So I'll show you a few of these plots in some form or another, where you see the evolutions of the observing strategy on the x-axis as a function of time. Typically, we benchmark key versions of the baseline. 1.x means earlier than version 1.2, where things infrastructurally were a little bit different and the baseline was fairly new. So you can think about like that as the starting point. And we are obviously at the end. The last three simulations are versions of baseline 5.0. The one that I've described is itself, baseline 1.0. We also have a simulation with 4 rolling cycles, baseline has 3, and we have a simulation with 2 snaps just to be on the safe side, and also to see what is the comparative improvement that is brought on only by the fact that we have changed to 2 snaps. So you see a lot of things in this plot. There is a line for each filter. You don't see a very significant improvement to the median co-added depth from earlier simulations, but you see an overall improvement from the beginning of the survey. There's also some key features that might jump to your eye. Those corresponds to when we updated the throughput with the change to the filter coding choices, and when we realigned the downtime in the simulation to a realistic downtime for the observatory. So those are the 2. Yes. Yes, absolutely. But do you need a microphone? Yes, you do.
Sorry, just to read this plot. Positive is good or bad in this plot?
Positive is good. That's the median co-added depth.
Okay.
And so you see, for example, at the end, with the 2 snaps, we go a little bit shallower because we have that 6% drop in efficiency, or rather that 6% pickup in efficiency with a single snap. Okay. What did I want to show here? So yes, just to add that we generally produce these simulations with weather stochastic ensembles of simulation with stochastic weather patterns. So you can see this gives you a sense of the uncertainty. The plot that you're seeing here is the proper motion for the best 18,000 square degrees. But I think this is here just to give you a sense of the uncertainties. And also you see the 2 key events, the change of throughput and the realigned downtime in more or less all as features in more or less all of these metrics. Some key changes over time that have caused massive changes in science metrics include significant changes to the galactic footprint at the beginning. So retro baseline 2.0 corresponds to that 1.x. So it's what we started from before we involved the community. We have made massive improvements in galactic science altogether, thanks to tweaks to the galactic footprint. We have massive improvements in solar system science, particularly adding the twilight time survey. And another significant improvement was when we started taking the pairs of images that are taken within 30 minutes. Each visit is taken in a pair of 30 minutes. That's primarily for solar system identification of asteroids, but it does have a significant improvement on some science, including transients. So we had significant improvements there too. This is a slightly more complicated plot, so let me guide you through it. On the x-axis, we have, same as before, different simulations over time. And same as before, the last 3 are the simulations that we're presenting and introducing today. Baseline, the actual baseline is this one, which is now circle. And in these heat maps, blue is good and red is bad. All these are relative quantities. So these represent improvements from one opsin to the next for given science metrics. If you see blue, that's good. If you see red, that's not so good. And neutral is baseline 5.0. So everything is relative to the current baseline. So when you see in the past it was red and now it's bluer, that's great. But it's a little bit of a mix. But mostly it's a mix because of the reasons that I explained earlier. Change of throughput and realigned expectations for downtime. This is a typical plot that the SCOC, the Survey Cadence Optimization Committee, would look at every time we have a change, a new simulation or a change in the survey strategy. We have key science metrics here and some system metrics. You can generally sort of grossly split this plot into solar system metrics at the top, galaxies, including local volume, dwarf galaxies, and number of galaxies, Milky Ways here, some time domain, transients, and variable metrics are here. Cosmology metrics are over there, and these are some system metrics, proper motion, parallax. And what is FO? And I always forget. Shelko's magic number at the bottom. All right. So, medium rate of TDC? Say louder. Strong lens. Yeah, I don't know. It's related to strong lens. Okay. But what is TDC for? Just right. Time delay cosmography. Any other questions or any of these metrics? Yes, John. The last 3 columns are, so the circle one is the base, the one that I highlighted is the baseline. And then 4 cycle baseline, identical to the baseline, but with 4 rolling cycles instead of 3. And baseline, but with snaps. 2 snaps, not 1 30-second exposure. 2 15-second snaps, just to keep track of the game. We're not saying we're gonna even, you know.
Sorry. And we should see these as metrics for the end of the 10-year survey, or this?
Yes, these are metrics for the end of the 10-year survey. Not that we don't look at metrics at intermediate years, but this is sort of like a comprehensive view. Any other questions? Anything on Slack? Anything on Zoom? We're gonna keep going. Okay, so, well, maybe before that. So again, here you see the change of throughput. When we updated throughput, the depth of most filter except U-band improved. So you see this drastic improvement. Things got blue because we improved the throughput of the system. And then here we realigned the downtime with expectations, so everything got red because we have decreased the efficiency of the system. In between these two, we also have updated the exposure time for U-band to 38 seconds because the throughput changes had decreased the depth in U-band specifically. We compensate that with a longer exposure in U-band to realign it to the expected ratio of depth across the filters. And so you see that generally, like I want to give you the impression there is some blue, but in general, it's much redder in the past than it is today. So overall, I want to recognize that the Survey Cadence Optimization Committee and the community at large have done a fantastic job of improving things across the board. All right, so this is a breakdown of what the survey strategy, of the elements of the survey strategy. What does the scheduler spend time on? The majority of the survey strategy is the primary survey mode. It's pairs of images separated by 33 minutes, so we can spot asteroids across the wide fast deep footprint. They're collected in pairs of filters. So in addition to spotting asteroids, we can get color for objects, including color for things that change in time on time scales that are not faster than 33 minutes, of course. And we spend the majority of the time here, 65%. Some of the visits are collected in 15 minutes pairs. Then we have a target of opportunity program, which at the moment in the current simulation takes 3.7% of the time. We have the deep drilling fields that take 6.1% of the time. We have 4% of the time spent on long gaps. So that's a third image, a third visit to the same field in one of the two filters that were used in the pair that allows for time domain science on transients that are evolving on time scales of hours and a few days, which otherwise would be lost. And it's very dear and near to my heart. I really like that feature. And then we have an interior twilight, Earth interior twilight survey that spends 1.4% of the time. Everything that is left, the scheduler just takes images as best as it can. That's the greedy algorithm at the bottom. And in this simulation, it's 6% of the time. We're going to highlight two of the elements of the current survey strategy. One is the target of opportunity. There are some small changes to the target of opportunity program as it was in baseline 4.0. But really here, I just want to highlight that we have a target of opportunity program. It currently takes 3.7% of the time. This is in slight excess of what the SEOC had recommended in PSTN 055, which was our earlier recommendation, which was 3%. We're not really worried about that. This is, we're responding to events, so this is highly stochastic. And the majority of that time is actually spent in later years on the survey when O5, LIGO Cagra Virgo system, comes online. The TO program is responsive to gravitational waves, as well as neutrinos for multi-messenger astronomy, and for potentially dangerous asteroids in a breakdown of time and with strategy for follow-up that was designed in a highly successful collaborative effort of the community at a workshop at Berkeley. You can see the report that came out of that workshop. People still come up to me and tell me that was the most productive workshop I've ever been to. So I'm very proud of that. We did write a report, which you can see there, which describes in detail how we should respond to triggers based on their nature and the information that we have. At the bottom, you see just like some just glance view of maps of how the observations are happening in baseline 5.0. Obviously, they're patchy because they're responding to localized triggers. And I've selected 3 bands at random, but you can see all the bands in the complete reports for the baseline simulations. And the TO program is already running, as you've heard in the plenary this morning. We have responded a couple of nights ago to a trigger from LIGO Virgo 04. It's a black hole candidate by the name of S250725. We have collected 54 good follow-up visits, which are being analyzed now to find counterparts. Black hole mergers are one of the science cases that we expect to respond to during operations in the TO program. Okay, I don't know what that is. I really don't, so we're not going to investigate. Next, deep drilling field strategies. We're going to spend a fair amount of time here. So are there any questions before we dig into this? Yes, John. Thank you, Michael. Appreciate it.
John Gieses. Does the TOO have a special data release policy, or do they just generate alerts like everything else?
Yep. So the data release, the data access, everything is the same as for the rest of the LSST survey. The reduction of the data, eventually you might need to have some specialized features. But at the moment, also the data collection happens in 30 seconds. So it goes through the standard pipelines.
Can I ask a question?
Please.
As well? 3% is sort of assuming exactly what O5 might do.
Yeah.
One could imagine a scenario in which there's less interesting objects to observe. If one observes less than 3%, I assume your greedy algorithm will take up the slack. There's nothing breaks if we go well under that 3%.
Nothing breaks. And also at the end, we'll talk about microsurveys. So if we are in sight of the fact that we are not spending as much time, that just opens up more time for either increasing the wide, fast, deep depth or doing microsurveys. Deep drilling fields. We have such good news about the deep drilling fields. So deep drilling fields, there's 5 deep drilling fields.
There's some questions on Zoom.
Oh, thank you. I don't see them, so please do interrupt me. The person that raised their hand, oh, two hands raised. Okay, Bindu, could you
Yeah,
unmute?
so I'm actually not familiar with this greedy algorithm. So can you say a little bit more about that?
Bindu, I couldn't understand you. Looking around, it looks like people couldn't understand you. Can you type it in the chat?
Yeah, sure, I can do that.
Thank you, appreciate it. And maybe Eric, if you can ask, if you can answer the question that is being asked in the chat. I had seen another hand raised, but it went down.
Said it was me, but I see that you're about to talk about the deep drilling fields a bit more, so I will reserve my question in case you already answered for me. Thanks.
All right, thank you, Wes. Bindu, we'll get back to your question after the deep drilling fields. Thank you. Okay, so there's 5 deep drilling fields.
So we have
We're ready for the
now.
question. Yes.
It's what exactly is the greedy algorithm?
So the greedy algorithm is filling in the time that is not spent on the other sections. It's greedy in the sense that it tries to take the next best observation that it can. So any time that is left after all the programs have been successfully run for the night, but cannot be run, for example, because you don't have 33 minutes left in the night. So you can't take a pair and you know that you cannot take a pair. So you plan for what is the best single image that I can take, right? I got it right, good. Okay. There's 5 deep drilling fields. These are the coordinates. The coordinates have been tweaked by the community. The selection of the fields have been driven by the community. These are fields that are highly special because they have a lot of multi-wavelength coverage. They have been historically observed by different surveys, so they will be observed or are being observed by current and future survey, like, for example, the Euclid deep fields. And so they're sort of legacy fields for astronomy, and we're going to contribute a legacy data set of LSST deep data. They take overall, as per recommendation of the SCOC, the DDF program takes 7% or less of the sky time. They're expected to have intense coverage, which is written down to be at least 10 times as deep as the wide fast deep in number of images. We'll see we actually go a little bit deeper than that. So there's different reasons why you may want to get this data on the deep drilling fields. You may be interested in just static sky, but really at significant depth. This will go down to magnitude in excess of 26 in R, as opposed to excess of 24 for the wide fast deep. Or you may be interested in having a high cadence because we observe them more. We also observe them more often. We can observe them for long sequences back to back. So you may be interested in the cadence aspect, or you may be interested in the depth aspect. So that means because they're multi-purpose, you know, there's various desiderata that different communities and different science cases may have on how to observe the deep drilling fields. At a high level, we want continual monitoring over the entire survey so that you can get the time evolution of things in there for a decade. That also means we want generally long season length, so you can monitor them for as much time as possible and see different time scales of evolution. We also want to have obviously much greater depth. So this brings some tension, right? So for some science cases, you may prefer continual monitoring over the entire survey with long season length, but that would be shallower, maybe less optimally designed to get across time and seasons to get the deepest data. This is something that might benefit, for example, the AGN community. Or you may want greater depth to go higher redshift and maybe even high cadence to see things like supernovae at high redshift and monitor them effectively. That may be something that the supernova cosmology people may want. And I point you here to 2 papers that describe exactly this kind of desires for the deep drilling fields, and that have largely helped us design the current strategy. So We knew that that the survey strategy that we had implemented in earlier baseline was fairly vanilla on the deep drilling fields, not particularly tuned to do anything other than collect 10 times more images and do the high level requirements that I mentioned earlier. So with PSTN 055, even a little earlier than that, we have instantiated a task force within the Survey Cadence Optimization Committee, courageously led by Saurabh Jha, who did a fantastic job and a really significant amount of work on this to define what should be the detailed strategy with which we observe the deep drilling fields. And some high level of recommendations as this task force came out with the previous baseline, including recommending that Cosmos will be observed to 3 times the depth of the other fields, full 10-year depth in the first 3 years, and then continue to be observed for the rest of the survey, as well as the fact that each field should be observed for all 10 years of the survey, and the inclusion of the Euclid deep fields as the final selected deep drilling field. Okay, but now, thanks to the task force led by Saurabh Jha, we have a new concept for how we observe the deep drilling fields, which we call ocean. It's called ocean because it can be both deep and shallow. So the idea at a very high level is that the ocean survey strategy has deep seasons on each of the deep drilling fields, but also shallower, still much deeper than the wide fast deep, but shallower than the deep drilling seasons, coverage throughout the lifetime of the survey. We could visualize it as something like this. This is the XMM LSS field. So you see in the number of visits to the field increasing over time for the entire duration of the 10-year survey. But in the 4th year, you see a spike, a jump, because that's the point when XMM gets a deep season with a whole lot more images than in the other deep season. In the desk community, these have been called the ultra deep field season. Again, a reminder, shallow here is still deeper than the wide fast deep. So the shallow season are already deep drilling fields. And then each one of them gets an extra deeper season. So the sequence length is, well, you see some statistics here. You see the alternation of filters and sequence lengths and the frequency. We observe them every night or every other night. The Cosmos fields is special, and also this might help you understand again how the ocean works, because it gets 3 deep seasons. In the first 3 years, Cosmos get deep seasons every year. It also gets the edge of the season gets observed as best as possible when it's on the sky. So you see this slight ramp up and then these plateaus when it gets off the sky. So far, so good? Cool, cool, cool. At this point is when I pass it to Peter for more details.
Okay, just to emphasize and try to visualize how we're changing the deep field strategy. Here's what do we got? We got XMM. This is our previous DDF strategy. I'm just plotting per night, color coding by filter, how many observations we're taking. And so this was just a very regular cadence, very deep. You can see we're doing like 80 visits total in a night, spaced out a lot. Going to the ocean for a shallow season looks like this. So you can see much higher cadence, but much shallower. Now we're only getting kind of 10 to 12 visits per night, but we're doing it much more regularly. And you can see we've got a total of 853 visits, whereas before we were doing 2,400 visits per year. And so those extra visits that we're shaving off are going to go into that deep season when we really hammer this field. And then we're doing variations on this as well, where we're doing what we're calling accordion, where some people still want deeper, higher cadence in the middle of the season. So we're going sparse at the beginning and end and denser in the middle. And so these are kind of requests from AGN and other folks who want that higher cadence. And so just blinking back and forth, you can see, oh yeah, we're getting denser, higher cadence in the middle. And a few more visits are needed when we go to accordion, but still we can go extra deep. All right. So here's kind of the giant table of how we're doing. We've got around 20,000 visits per field, except for Cosmos, which is going extra deep. And then the Euclid Deep Field South is a double pointing. And so its visits get split between the two positions so we can cover the entire Euclid field. Anyway, so we've got our positions, we've got, and you can see the evolution of, and we're running various DDF experiments. So we're doing our accordion experiments. We're also looking at options for spatially dithering the DDF fields. We'll get to that in a second. So, and here we are, we've got our baseline. There are the ratios of the different filters we've currently adopted. In the accordion, we've bumped up U a little bit on request. And so to some extent, we're flying blind a little bit. People are requesting more U, but we don't have great science metrics like we do for the main survey. So it'd be great if people could come up with some science metrics to help guide us on which of these is better. We don't have those great plots like we did for the wide, fast, deep. So if people have ways to say like, yes, that extra U-band coverage is helping my science, or no, it ruins my science, that would really be great. All right. And here we're giving the deep seasons, we're spreading them out through the survey so that, obviously we don't impact the wide, fast, deep survey too much. And intentionally, we're doing these earlier in the survey. So if there's a terrible season with weather, if there's a terrible season with engineering downtime, we can bail and say, oh, let's not do the extended Chandra Deep Field South in year 3, let's put that off and we can put it in year 7 or 8. So we're sure we have time where we can bump these to later in the survey if we need to make sure we get that extra deep, ultra deep season if we need it. All right, so we have variations. And usually we're doing ultra deep seasons in year 1 for both Cosmos and the Euclid field. That's to try to synchronize with Euclid while it's flying, and also getting ultra deep early so we can do the analysis on Cosmos and get the coads, and that way we can be sure for our later seasons we're optimized on our dithering pattern and we're not going to hit anything odd. So we definitely want to get the Cosmos ultra deep season early as kind of a precursor to make sure we've optimized the strategy for the others. All right. So we definitely have questions about these deep drilling strategies that we want feedback from the community. So, the timing of when we should do the deep seasons, a lot of people are pushing for earlier for synergy with other missions. We're flying a little blind on the filter balance. So we'd like, specific science cases for figuring out what the best filter balance is for these deep drilling fields. And U and Y band, because they are not loaded in the camera all the time, they are a little extra tricky to schedule. So figuring out, you need to be more flexible with your U and Y cadence. We can't do U band every other night or anything. And then we're also working on AGN specific feedback. So, can we get enough depth, or do we need to do those accordion things? So we have resources. Runs are up online at USDF. Hopefully you're not blocked anymore. It was obvious USDF thought we were doing a denial of service attack from the hotel last night. So you couldn't log in. I think they fixed it. I think we're back.
To be clear on the filter balance, we're following guidance that are scientifically driven from the science collaboration, particularly the desk and the AGN science collaborations have been outspoken about the filter balance that they want. What we don't have are metrics that science-based metrics that show what is the scientific throughput of changing that balance.
Yes, and we have a great supernova metric from desk, but one of the weaknesses, because they're looking at higher redshift supernova, they're not very sensitive to U-band. And so if I put more U-band in, that doesn't change their metric, and I don't have anything else to say was adding that U-band good or not. So we do have some metrics, but definitely need more. All right, dithering. There's definitely tension with how we dither the deep drilling fields. Our default for a long time has been to pick one position per night and not dither within a night. So that's one. And then of course the size of the dithering, most the astronomers want small dithers. They just want to fill in the chip and raft gaps and not dither too much more. Data management is very concerned about stray light and systematics and being able to co-add things. And so they tend to want larger dithers to make sure they can get rid of all the artifacts. So we're investigating both. There, on one side is the final co-added depth of Cosmos with very small dithers, but still including rotational dithering. And then on the other side, you can see a huge gradient when we have to do much larger spatial dithering. And so again, we're expecting what we'll have to settle on is somewhere in between these two. Data management would probably like that. Astronomers would like that. But we're going to have to figure out what we can get away with. And again, metrics would be great to say, how urgent is it that we go to those smaller dithers than the nice, smooth, larger dithers. All right.
We can take DDF questions. I think
Oh, yeah.
actually before that, I wanted to ask Sorabi if he feels like we represented fairly the work of the task force and the ocean strategy.
Yep, great. There were some typos on the slide, but we can.
Any questions on the deep drilling fields? Michael.
So I want to ask a bit more about this dithering question. How adamant are our DM friends on this question of dithering? I mean, if they say, if you do dithering that's smaller than 0.8 degrees, the data are unreducible, then that would sort of answer the question. I wanted to, I mean, just as you're asking for metrics on the science side, you also want to find out just how strong that barrier is on the DM side, as it were.
Yes, we are actively asking them, and obviously we're just starting to take DDF-like observations in commissioning, and so it's an active area of research.
So not only we're actively asking, but the survey strategy for the deep drilling fields that is currently running on the science verification is a very modified ocean survey strategy. And we are testing dithering strategies at the moment before the renovation of the zone that will happen in September. Buffalo and Straylights, there's more issues than we expect there to be with Straylight during actual survey. So at the moment, the situation is slightly worse than we expect it to be. The question is, how much will it improve and what will be the residual Straylight? I had seen Vincenzo, then David, now lots of people. Let's start with Vincenzo. David, you're right.
Yeah, first of all, I want to thank you for this work because really it is terrific. I can just imagine how complex it is to put all the metrics together and evaluate the best thing for multiple groups. Just a suggestion, as the shallow seasons for the ocean strategy are still deeper than the wide fast deep, I would propose to call them deep and ultra deep, because when people are reading, the messages that you're putting on the community forum, they might complain a bit if they see shallow. And then if you look, it's not actually shallow. And in one of your slides, you were showing that it is like 2 times deeper than wide fast deep. But are you referring to the rolling cadence or the non-rolling?
Good question. Yeah, probably the average.
Yeah, the typical shallow, I agree with you, Vincenzo. The typical shallow visit is either 2 or 3 visits, right? And the typical wide fast deep is 1 visit. So it is 2 or 3 times the exposure time per epoch.
And the DDFs are included as part of the wide fast deep. So they will get wide fast deep visits as well. These are all on top of that underlying survey.
Hi, Fed. Wow, you guys do all this amazing work. So on the first day, Željko talked about how the image quality is not quite where you want it to be yet. So how does the image quality play into the survey cadence? And are you modeling this as well? The ultimate image quality of the survey.
Right, so it folds in, so the scheduler is thinking about image depth every time it takes an image. So as if the seeing gets worse, it knows it should avoid high air mass even more than usual. So even if part of the survey has fallen behind, it'll say, oh, image quality is really bad. I don't want to go and chase that. I'm going to wait for better time. So we can't solve atmosphere with software, but we do what we can.
Regarding the dithering for the deep drilling fields, certain people within DM are more worried about the stray light. Some of them are at Princeton, and Michael, I recommend you talk to Robert Lufton. I am more optimistic, but at the same time, I, for calibration, would prefer slightly larger dithers, more spinning things around enough. But I think the only thing we can really say is we need to test one of these strategies in commissioning. And I've always been told that is on the agenda, but we haven't done it yet.
Yeah. So
Tony and then Rachel.
Just a point on this slide, I never got into trouble observing and dithering by taking big dithers, but I've gotten in trouble with systematics with little dithers. And so I'll bet you if instead you ask the astronomers on the left there, if they would be willing to have data that is in systematic error, this would look different.
absolutely, yeah, it's.
So Rob, do you want to comment on that?
Sure. I mean, you know, there's many different science cases. There's sort of the long-term legacy value of the static co-added, but there's also the, you know, I want to measure my supernova on this night. And those are different systematics about what the background, you know, how well the background needs to be dealt with. I think the hope is, I think everyone, you know, agrees that large dithers are probably useful to do. And the question is just how many do you need? And, you know, as Peter showed, that these fields are going to get 20,000 visits over the 10 years, typically. And the question is, how many of those need to be taken with very large dithers? And we don't know the answer to that. And Keith had a very nice comment in the chat. You can look at that, you know, people are doing the tests right now, but it, you know, it could easily be the case that it doesn't have to be all 20,000 visits have to have large dithers. And just having building up some small fraction of that with large dithers allows you to get the sky background to the extent that you need to do the, you know, to do all of that corrections and remove those systematics, you know, well enough. And so we might be able to do it all, and people are working on it.
Hi, Rachel Street. I have a question about ability to coordinate with other key surveys going on contemporaneously with Rubin. I'm particularly thinking of the Roman mission, who recently issued a pretty comprehensive report on the survey strategy for the core community surveys and what scope we have to coordinate some of the Rubin and Roman observations for the maximum science return.
Yes, coordinating with Roman is on our list. You know, it's not listed in there, but I think we have a 0.2% or 0.02% pseudo DDF for Roman in the bulge that are in all the simulations, but they're currently a placeholder so that we can move those around and do fine-tuned coordination with Roman.
Could I also mention, because I know a little bit about that report. But yeah, so this is one of the things where the shallow seasons, or however we want to call them, you know, they get all these fields all the time, essentially. You know, whenever Rubin can observe these fields, those are going to be observed. And then it's a question of the deep seasons, you know, what depth do you need to match other facilities? So I think for anyone's ground-based observations, these fields will, you know, being observed all the time that Rubin can observe them, you know, they'll go to 24th to 25th magnitude per night in the shallow, quote unquote, seasons. And for most ground-based observatories, that, you know, that should be really plenty, right? It's going to be hard to do much deeper. For the deep seasons, where the deep 100 sequence visits get you to closer to 26 magnitude per epoch, that's where the synergy with the space missions is probably most you know, likely. So for Roman, for instance, the high latitude time domain survey includes the Euclid Deep Field South as one of its time domain fields. And so the question for those is that there's only so much deep time. Right now, the EDFS South is observing year 1 for good Euclid overlap in time, but actually Euclid will be observing those in year 2, 3, and 4. And so there's a question about, you know, should we add some more deep time for those seasons? And then even further on, as you mentioned, Rachel, with Roman, we'll be observing those later on. And so there is still scope to do more of the deep kind of observations, but there is a limit of the budget of the DDFs. And so that's something, you know, we're going to have to consider what are the best commensal observations. But I would emphasize that this shallow is already pretty deep. It's going to happen every other night in basically all the filters, all 10 years, all the fields. And so if you're okay with depths of 24th, 25th magnitude, that's covered. It's just going deeper than that. That's going to be harder.
Wes has a question online, and then I'll go back to Tony.
Hello, sorry for not being able to be there. Just a question about the, I guess you're commenting on this a little bit just now, but what is the sort of cadence in the deep, let's see if I can get the jargon right here, the deep or the ultra deep or the phase where it's the deepest. It's all a mess. Because I'm thinking about, shift and stack for moving objects, which does have some somewhat specific cadence requirements. Yeah, so like exactly right here, XMM, I'm also thinking about the Cosmos field, which is the closest to the ecliptic. Is there any room to provide some input about how often these fields are visited and how they're visited, or is it just like they're going to be visited all the time, or what?
So yeah, currently it's pretty much all the time there. We are limited by the moon. When the moon comes by, we
Of
don't want
course.
to observe it. But other than that, yeah, it's those ultra deep seasons are pretty much nightly. They're getting observed.
But is it like nightly with 5 exposures or nightly with 500? I don't.
With a little over 100. So the deep sequence will be 4G, 18R, 55 in I, 52 in Z.
So in this slide, you see the observing strategy for an epoch of shallow at the top and of deep in the second block of
Okay,
text.
but yeah, so these are nightly. That's the word. That's not
Per night, and
either.
one epoch being one night, one time they will go
Good
visit
enough.
them.
Great, that's perfect.
And
Thank
then
you.
again, they're visited daily or semi-daily.
It turns out to be more like 1.5 nights cadence rather than nightly for the deep sequence.
It'll be 200 of those sequences spread out over a 225-day season or something like that. Yeah.
Thank you.
And there's some losses to weather.
Yeah, I just wanted to point out that there's another kind of dithering that goes on, which is rotation. This is because our CCD sensors have a systematic bias in one direction, and you want to spread that around plus or minus 90 degrees. So you have to rotate as well as dither and angle.
Yes, and so every night we pick the scheduler picks a preferred rotation per night between plus and minus 90, and you can if you look really close, you can see a little green circle on the node dither, and that's the fact that it's not a pure circle. So those are the rafts that are missing on the corners, and because of that spinning, it means that that annulus on the outside doesn't get quite as deep.
We're going to move on to templates.
Okay, so one of the things lots of people have asked us for the scheduler is how can we get image differencing templates as fast as possible, because we want to get the alert pipeline going and start detecting things. The current plan is that templates will be built incrementally. So we'll observe for a while, then data management will generate a template. And we've run lots of simulations in the last year, especially looking at can we speed this up? And in general, it's hard because our baseline survey is really good at gathering templates. It's scanning the sky as fast as it can. And so if we say, okay, stop doing that and start gathering templates, it pretty much does the exact same thing. We can't speed things up. We have to wait for fields to rise. We have to dodge the moon. We just can't get templates that much faster if we turn off the main survey. So we've checked a few things, especially with the North Ecliptic Spur. That is one area where it's a small enough area and it's not all 6 filters. So we might be able to blitz and get the NES a little bit earlier without impacting the rest of the survey. And of course, we're practicing with the SV survey, the commissioning survey right now. And we're trying to figure out just how strict we have to be on when can an image be used for an image template. So we already had questions about the atmosphere and image quality. So we're trying to figure out exactly when can things count as a template, and we're folding that in actively now so that we can say, like, do we need to insert another layer in the scheduler to say, yes, try to get image templates. So, for example, when the seeing gets really good, should we switch and make sure we have good seeing images across the entire sky? So we're checking now to see if we need to do that.
I can talk. Questions about the template? So year one the current plan is that year one will proceed, except for the North Ecliptic Spur, more or less the same as the rest of the survey, because that is an efficient way to collect templates. So the modifications of the survey strategy in year one, as recommended by the SCDC at the moment, are minimal. The last topic that I want to cover is microsurveys. This was actually requested to be discussed by some community, including the Solar System Science Collaboration. Thank you, Kat, for bringing that request forward. So let me define what a microsurvey is. A microsurvey is a survey within LSST which observes the sky in a specific way designed to achieve a specific science goal, which is different from the wide, fast, deep, or deep drilling fields or TOs. And that takes less than 3% of the LSST sky time. So with the extra time that we have after we've implemented all the observations of all the programs that you've seen, what now the telescope does is take greedy observations. Let's get the best next visit that I can possibly get as a single visit. But that time is in a way accessible to conduct surveys that are specifically designed for some science goals, and that can be community proposed. In section, I don't remember what section, of PSTN 055, which was our phase 2 recommendation, we had already received a number of suggestions for microsurveys that could be conducted, and we reviewed them and established criteria for what we should seek in a microsurvey to approve it. Specifically at the time we were thinking to approve it on year 1, but this sort of like time urgency should remain as a consideration for microsurveys, because we intend to open proposal calls for microsurveys throughout the survey. So is there a next scientific loss if we don't do the survey in the next year or in the next 2 years? This was a very clear case, for example, for some solar system suggestions because of the increasing number of artificial satellites on sky that may interfere with solar system observations. Does it take advantage of the unique features of Rubin? Does it require, for example, the depth of Rubin or the field of view of Rubin or the ability to scan the sky rapidly of Rubin, or can it be done with another survey, with another telescope or another system? And obviously, does it have a well-justified and worthy scientific benefit? At the time, the SEOC reviewed upwards of 10 suggestions, 10 proposed microsurveys, and identified this one as the critically timely one. And so in version 3.0, in baseline version 3.0, we introduced the near sun twilight microsurvey, which then got subsequently slightly updated, and you see it now in all of our simulations. We expect to issue more calls for microsurvey, as I was saying, and we expect to issue the next call for microsurvey during year 1. We are targeting roughly 6 months into LSST to release the call for the microsurveys and give a couple of months to the community to submit microsurveys, which we then can review in a couple of months and make a recommendation as if something needs to be done or should be done in year 2. These 6 months will give us a better understanding of how the system is performing. So it will give more ammunition to both the survey cadence optimization community to review knowledgeably whether the microsurveys are possible, what the expected throughput would be, as well as for the community to tune the strategy that they recommend for a specific science case. So expect an open call for microsurvey roughly half the way through the first year of LSST, and expect to be due proposals to be submitted within a couple of months of that call open. You're very welcome to resubmit. I think I might have been moved. No, you're very welcome to resubmit proposals that you had earlier submitted to the SEOC or the SAC. These are the 10 that we had reviewed. 9, I guess, that we had review in PSTN 055. In many cases, we gave suggestions on why they weren't immediately selected, and you should obviously address those suggestions and update these to the current scientific landscape or our proposed brand new surveys that responds to brand new scientific priorities. That's all I had to say about the microsurvey. I had this very, very cheap graphic to just sort of give you a sense of the timeline, where we are and where we're going. So right now we're conducting the science verification survey. This is the longer blue line in this plot. And we have just released baseline 5.0. So we are right there in this slide. So we expect the survey to start in late 2025, possibly late 2025. I do recommend that you review what was discussed yesterday in the early science program session for more details on that. And during year one, after about 6 months from the start of the survey, we'll open the microsurvey proposal call, and towards the end of year one, the SCOC will issue a new recommendation for tweaks to the survey strategy. As a reminder, the Survey Cadence Optimization Committee is a standing body of Rubin Observatory that will continue to issue recommendations to improve the survey strategy throughout the life of the survey, so that we can be both responsive to new scientific priorities as well as system response. Questions on that? Questions online? Okay. We do. Oh. And did we answer Bindu's question from earlier? Yeah, we did. Bindu, you want to try to unmute and see if we can hear you this time?
Okay.
Sounds about right.
Can you hear me okay now?
Yes.
Oh, hi. So I actually was wondering, so how long does it take for the science verification survey data to be released, like within the collaboration itself?
Leanne, do you want to take that one? This is not a survey strategy optimization committee question.
I think so.
Let me just repeat the question because the sound was a bit muffled. Were you asking how long does it take for the science verification data to be released to the community? Was that the question?
Yes.
Yeah.
Yes.
Okay. So the science verification data that Fed's talking about now that we're collecting currently with LSSTCAM, we plan to release that as part of data preview 2. Our estimated timeline at the moment for that is sometime around mid to sort of Q3 next year, July to sort of August, September next year. But that's still a rough estimate. We haven't collected all the data. We haven't started processing it. So please, bear in mind that that's an estimate that we will update as we collect the data and as we understand the characteristics of it.
Okay, thank you. So there is another question I have about the micro surveys. So for us, what the requirement is to have the observations, continuous observations in one field, and the idea is to use the longest possible night. If we wait for the micro survey call, then we might miss the opportunity to be observed in the first year of Rubin observations. Although this is not something like, it can be done in the second year as well, but I'm just trying to see during the science verification survey observations, is it possible to use one night for any particular kind of crazy science ideas?
So I'm here to talk about the survey strategy during LSST. So I'm not speaking for science verification. During LSST, that would look like a microsurvey. So you would need to propose it as a microsurvey, and you would go through a vetting by the Survey Cadence Optimization Committee and a recommendation process. Make sure that you demonstrate that that's something that can uniquely be done by LSST, because a lot of telescope can easily look at the sky for one night consecutively. So why LSST? Is it the field of view? Is it depth, etc.? And that would look like a microsurvey. So yes, we're not going to include new microsurveys in year one. So the soonest that we would consider that is within the proposal opening, the proposal call that I described. So it would be for year 2. Could it be included as part of science verification? They're saying science verification is for verifying the system. So we're not doing specialized surveys for science in the context of that. And I thank Leanne for shaking the head and help me get the right tone to that answer. But indeed, it is a good candidate for a science verification, for a microsurvey. And in fact, there was a question on Slido, which I think is possibly, Bindu, I think you might have contributed to this question, which was along the lines of, can we do a survey strategy that is similar to what was done in commissioning, because it was demonstrably good for variability, YSO, Cepheids are lighter cataclysmic variables, transient planets, yes, that would be a microsurvey. And so the process that I described for submitting microsurvey applies here.
Okay, thank you.
You're very welcome. I think that was the end of our presentation. A list of interesting simulations that I don't want to presume, a list of simulations that might be interesting to you, including the 3 variations of the baseline that I've described, the deep drilling fields, variations of dither, additional variations of the deep drilling field ocean strategy as described. We're also still actively investigating some of the parameters of the deep drilling field ocean strategy, filter balance, specific depth, when to take the deep season. So there will be more simulations coming up that are variations on the deep drilling strategy. We have template collection simulations, particularly for the north ecliptic spur, north ecliptic spur, which Peter has described. We also have simulations where we prioritize one band for template collection across the entire sky, and we will have more. And all of those come in sets. We do have, or many of those come in sets. We do produce sets of simulations for each of the key simulation that represents variations on weather patterns, so that we can ensure that the throughput and advantages that we see with the simulation are robust to stochastic events. And resources, and that's the end of the slide deck. So the floor is open for question for another few minutes. John.
I hope you don't reject this as being outside the bounds of this one, but one of the micro surveys that you showed there was a short exposure idea. And so I was wondering, because clearly any such proposal would be informed by actual LSST short exposure data. Are there in the science verification program short exposures or even different exposure times? 5 seconds, 1 second, 10 seconds.
Peter?
Not as part of the SV survey. I'm sure as part of commissioning, they're taking different exposure times. Yeah,
Yes.
Yeah. So I'm sure they've taken those, but yeah, we're not taking those in an automated fashion. So
I think Chris Stab would murder a few people if those are not taken as
Exactly.
part of commissioning. So I'm pretty sure that. If the Chris is there. Well, let me improvise an answer that says, if those require specialized data management processing for releasing, that is, we're adding work on work on work on work. At some point, work needs to stop being added. Who wants to go first?
Yeah, so I've long been an advocate that we start the survey in much brighter time than I think has been assumed. There are 2 technical limitations. One is there's a limit to the flux that we can put on the detectors and not trip the high voltage bias. And the second is if we thrash the shutter to death, right, that doesn't work. And there's a thermal limit on the rate at which we can take exposures. So those are sort of technical limitations. But having said that, I think there's a really strong scientific case that we basically operate at constant sky brightness, start as early as we can, and take increasingly longer exposures until we hit the 30-second asymptote, and then continue out the other side in the morning twilight, right? And that extends the dynamic range to the bright end, gets us peaks of light curves, better match to Gaia, all kinds of good reasons to do this. It's a little bit in tension with the solar system people who want to look right down the Earth's orbital vector during that twilight time. But I think these colleagues who are working that arbitration can manage that. And we now have, I think, thanks to Alana, Peter, and others, good measurements of how the sky brightness evolves as a function of solar angle. So I do think we should open up our thought aperture to thinking about doing that.
And formally, that would happen through the micro survey process, or at least that could be pursued through the micro survey process.
that could be pursued through the microsurvey process. There's also engineering time. So if it's an engineering question, that will go through the engineering time. If it was a science survey, that could go through the microsurvey process. Also, like I described the microsurvey as covering the extra time. That's the extra time in the bounds of when we operate the telescope now, right? But the process, I think, I envision will be the same. Do you want to add anything?
Just in terms of what we would include in a data preview or release, we aim to include everything that's useful that's taken during commissioning. I mean, we don't want to remove data that could be useful. At this point, I'd say that we're not including donut images, for example, or AOS testing engineering images, for example, and we're only really putting a cut on images that have image quality that is too poor to really do any science with and to not include. And we're pretty generous with that right now. So a priori, without actually having seen this data and processed and looked at it, we wouldn't exclude it if we thought it were useful and we could process it, include it in DP2.
More questions? Online questions?
Sarab points out that along the lines of what Chris Stubbs is saying, should we observe through thick clouds to get the brighter things and basically use the clouds to
I do not see a lot of enthusiasm for that suggestion, Sarab. Yes.
Thanks. Brian Miller. What is the current spatial dithering pattern? Is it grid or spiral?
So for the DDFs or full sky?
Or I guess for both.
So for the DDFs, we pick we draw a random number between 0 and the maximum and a random orientation and do that per night. For the wide, fast, deep, we have a tessellation of the full sky, and at the start of the night, we randomize that orientation. And so every night we have a different full sky, covering. So, and that works really well because our tessellation is similar to a soccer ball tessellation or the geodesic dome at Epcot. So there are a couple spots where it's a little bit denser. And so those dense spots get perfectly randomized over 3,000 nights. So we don't end up with, it ends up very smooth.
So for wide, fast, deep, then most of the dithering is in rotation.
It's complete.
Yeah.
There's a grid that gets completely randomly oriented.
Okay, thanks.
Other questions, thoughts? Well, if there are no other questions or thoughts, you will see us again as a team at the session this afternoon on how to monitor the survey strategy during operations. So please come and join us there and ask the questions about that there. Bye.
Thanks.
Thank you, people on Zoom. I'm going to stop sharing
software. We've never, at least many of us have never gotten funding in any way to build the software infrastructure needed to get ready for Rubin, because science, all funding institutions want to see science, and so it's often hard. And so now when you have LSST running, they're going to be like, do science with it. And so then how do we do that? So there was an argument, the discussion that like link frameworks can be an avenue to really support that going forward, because we don't really know what the avenue elsewhere would be unless you can really hide something in your grant. And that most people will be like, cool, we built this thing, but now, maintaining it or going longer is not going to be something that you're going to be able to get much on. You'll be like, I hired a postdoc, but that wasn't the person I actually needed to help me maintain this when Python 4 comes out. So there was discussion of that. Also, understanding the needs, that there may be some mismatch in needs currently. Like there was raised about, there's link frameworks office hours, but often people don't show up. But maybe that's not what we need. What we need is you to come to our actual collaboration meetings. And if you can fund yourselves to come, because we have no money, we get some money, or we beg around, including LSSDA, right? But so if you can come to us, then maybe that's what we need rather than a monthly, office or weekly office hour. There was some discussion of the mid-year grants. So how do we do maintenance? We're building stuff, but how about in year 5? And that also, we're all maybe some of the science collaborations coming out of the firefighting mode of like, okay, this is as cool as we totally need. And then you're like, great, the data's here. What was all that stuff we said? Well, we got to push that aside because we had to get all these things done because it was important. So again, maybe it's pushing us to come up with a our phase 2 software roadmaps. What was the stuff we really would like, but we didn't dream of because we were like, well, you need all these other things first in year 1 and year 2. So maybe that's again something about ways of pushing the science collaborations or getting us together to think about those things.
Great. Well, thank you very much for everyone that came to the session. And let's thank our speakers one more time.